Hello everyone, this is Yufei Wang. I'm presenting our paper role, Self-Supervised Reinforcement Learning with Object Reasoning. This is a joint work with Gautham, Narasimhan, Xingyu, Okorn, and my advisor, Professor David Hill. Reinforcement learning has been successful for many robotics tasks. However, applying RL directly to real-world robots with only camera sensors remains difficult because we have to infer a reward from images. For example, it is very difficult to estimate the object positions in this messy kitchen with cluttered background and occlusions to give the reward for manipulating the objects. Prior work has proposed to first learn latent space and then use the distance in the latent space as a self-supervised reward. Given a current image observation and a goal image, this work uses a VAE to encode them into two latent vectors, and then use the distance between these two latent vectors as a reward. However, because the VAE encodes the whole image, there are some drawbacks in using such a reward. First, the arm information is encoded into the VAE latent space, and thus the reward derived from the latent space will account for the arm position. Second, the static background is encoded into the VAE latent, but it gives no information for the target object to manipulate. Indeed, prior methods often fail to align the target object. Instead, they only learn to align the arm in a given goal image, as shown in this video. In this work, we propose ROLE, which stands for Reinforcement Learning with Object-Level Learning, that performs object reasoning when learning the latent space for reward. Specifically, reward should contain information only about the target object. We use segmentation to remove the irrelevant information such as arm and static background when learning the reward. Our segmentation is achieved by the following process. Given an original image, we first do background subtraction to obtain the foreground mask. We then obtain the robot mask by a pre-trained robot segmentation network. Next, we subtract the robot mask from the foreground mask. Finally, we obtain the segmented objects using the object mask. Note that this process requires no prior information of the objects and is thus called unknown object segmentation. However, other approaches of unknown object segmentation could also be used here. The diagram below summarizes our algorithm. Given a current observation image, we encode the whole image as policy input because the policy needs to know the relationship between the arm and the target object. However, for the reward, we first perform segmentation to obtain object-only image. We then use a separate object VAE to encode the segmented image. During training, the goal is sampled from the object VAE latent manifold, and the policy is conditioned on the object latent goal. Most importantly, the reward is computed using distance in the object VAE latent space. The reward is object aware, and it does not incorporate irrelevant information such as robot position or background. At test time, we provide goal image and perform segmentation on it. One possible issue of using a purely segmented image is that when there are occlusions of the object, the segmented image simply becomes empty. We solve this by performing occlusion reasoning. Specifically, we employ a lower training scheme and an auxiliary loss to make our method robust to occlusions. It works as follows. First, giving a trajectory of segmented objects. We add synthetic occlusions to an image in the middle of a trajectory. After synthetic occlusion, humans can still infer the path position from the previous path trajectories. Therefore, we use an LSTM to encode the history information of the path trajectory into the latent space. We add the matching loss, which is the L2 loss between each pair of latent vectors after synthetic occlusion in the original and the occluded trajectory. We want the LSTM to encode them as the same, so it can learn to use the history information to infer the object position and be robust to occlusions. Now, we present the full ROLE algorithm, which performs both object reasoning and occlusion reasoning. Recall we've already used a separate object VAE to encode the segmented image to compute the object-aware reward. To perform occlusion reasoning, we add an LSTM after the object VAE and use the aforementioned matching loss to train it. We then use the LSTM encoded latent for reward computation, which is robust to occlusions. Now we move to the experimental results. We evaluate ROLE on 5 Mojoko simulated visual control tasks with no task-specific reward. In all tasks except door opening, we see ROLE learns much faster and achieves better final performances compared with the prior method, skill fit. Below is a video for the learned policy. For each task, we give 3 different goal images. Note that our method aligns the target object, whereas skill fit often aligns the robot arm instead of the object. To summarize, we have proposed a new view self-supervised RL algorithm ROLE that incorporates object-level learning to improve reward computation and goal sampling. Use a novel matching loss and training scheme to perform occlusion reasoning. Learns dramatically faster with better final performances compared with prior methods. We thank DARPA, NSF, and LG Electronics for their sponsorship on the project. Thank you.